All right, welcome back, Cohort 5. We're in our first discussion for Chapter 7. So, Andrew, thank you for facilitating. Feel free to take it from here.
Um, first meeting on Chapter 7. So I'll do what I did with Chapter 6 and maybe just I'll attempt to give a brief rundown of the chapter outline and sort of layout and what's going on. That said, there's a lot going on in this chapter. And I would say, aside from Chapter 6, those who are interested in getting started on building active inference models are going to want to kind of give a kind of special amount of weight to this particular chapter. We are introduced to hidden Markov models and partially observable Markov decision-making processes, which POMDP is shorthand for that. And it's just, as of right now, that's kind of the not completely ubiquitous, but most widely used models for a variety of behavioral experiments. That said, a couple weeks from now, we'll get into chapter 8, where we talk more about continuous models. And that'll be for looking at instances where we're looking at very, you know, fast time scales, and great for things like motor movements, and just with things that are much quicker. But usually we're dealing with discrete variables. So chapter 7, quick intro, 7.1. We focus on models of categorical variables in discrete time with examples increasing in complexity. So we're introduced to models of perceptual processing, decision-making, info seeking, learning, and finally hierarchical inference. And the authors try to kind of get at different sorts of emergent properties, including measurable physiology and behavior from these models. 7.2, we're introduced to the hidden Markov model and a perceptual processing experiment. This is where the model is of our beliefs about how a musician's audible notes, which are the observations or outcomes in the model, are generated from a written musical score, which are the hidden states, the actually written notes. They simulate the dynamics of Bayesian belief updating induced by a sequence of heard notes, again, the outcomes. And then from there, it gets into, before I move on to the next section, it's just worth noting all of these experiments in this chapter more or less denote very specifically what are the hidden states, what are the outcomes, what are our matrices that we're looking at. The A matrix, or the likelihood matrix, probability of observation given state. Our B matrices, which is our beliefs about how one state moves to the next. From time step to time step, we have our D vector, which are our prior beliefs about states, just starting at time step 1. That's it. Once you move on from there, D is no longer, it's in the equation, but it's not repeatedly used at every time step, although it can be updated depending on how you're running an experiment, such as from trial to trial. So we get to see how it evolves over time. There are 5 total time steps. It's another thing important to note. A lot of experiments, you'll typically decide how many time steps occur or will occur over the course of your experiment. So here there are 5, a total of 5 notes that are played. Thanks, Daniel, for going to figure 7.2. I guess to get a little bit more in depth here, upper left of that figure shows the model's kind of posterior beliefs about states and its confidence. And so like these lines start to stretch outward at first. It's getting the right notes for time step 1 and time step 2. Suddenly at time step 3, we get an incorrect note, or at least an unexpected note. There's a difference between the observations, which are in the lower right corner. A certain note is played twice in a row incorrectly, versus what should have happened or what we expected, which is the top right graph. unless you can see that lightly gray square. That is, if the model correctly inferred the right note, the one that's in black, but it was thrown off by that incorrect note occurring. That's the gray there. So these are all basically outputs of the model as the experiment is run. At the time of this experiment, I believe they were using MATLAB and SPM as their kind of packages and software used for deriving this experiment. So there's a lot of nice functions for producing graphs and outputs of the experiments, so you can actually see what's going on whenever you run them. Moving on to section 7.3. Now we have what is arguably a really key sort of model to dig into. This is where decision making and planning are introduced into an experiment. And so now our HMM becomes a POMDP. This can be seen, let's see, figure 7.3 is a great one to, it's kind of a exemplar image of a POMDP, where we have many elements as we had before. We have our D vector, the initial states, starting all the way at the left. From there, we move on. We have our states, we have our outcomes, S and O. We have our A likelihood matrices, which map the two. We have our B matrices showing going from state to state. But now what we've done is we've added policies, which are sequences of actions that the agent holds. Like it could do this series of actions, it could do this series of actions, and so on. Those are all kind of scored, so to speak, by what's another quantity that's been introduced here, expected free energy, which differs from variational free energy that we've seen before, F, in that G now it takes into account preferences, which are also C, not imaged here, but you can see on the right, they are denoted in that like list of equations. And those impact how G is calculated. That is, you kind of are trying to score, should I do this to get what I want? Should I do this to get what I want? Should I do this to realize my expected or preferred outcomes, or should I do this instead? That is impacting how the agent from there computes its transitions. So what we've done is introduced action into the model, where action now impacts the environment, and it's expected to impact the hidden states of the world that our agent is inferring. So it's just kind of like the prior example, but now we've just added this whole new dimension of action, where there's an actual bidirectional relationship between the agent and its environment. We were also introduced to a couple of concepts whenever the authors break down expected free energy. So we have like negative epistemic value, and we also have pragmatic value. This relates to the famous exploration exploitation debate or dilemma. There's a broad statement in this textbook that active inference naturally balances out exploration and exploitation. That's its own kind of conversation to have, and some people debate that depending on how you want to define what balance means. The key point here is that exploration and exploitation, or epistemic value and pragmatic value, changing your mind or changing the world, are included within the same cost function. If you want to look at this from a machine learning perspective, for example, or more statistical perspective or calculus, what we're doing is that we're minimizing this quantity that is expected free energy, and you're minimizing it by engaging in both kinds of behavior. Both of them contribute to minimizing the same quantity. And I believe that is what is meant whenever they state that active inference naturally balances those two kinds of actions that an agent can take. We're also introduced to other things that, for the sake of time, I won't go too deeply into, but we are introduced to factorization here. So there are different kinds of states that the agent can try to infer There are also different kinds of outcomes or sensory modalities that the agent can try to infer. For example, that figure 7.4, the A1 matrix is just mapping the exteroceptive modality or set of outcomes, which is basically where the rat is in the maze. But then the second matrix, A superscript 2, is denoting the rat's beliefs about the stimulus. If there's no stimulus, an aversive stimulus, or an attractive stimulus. And so the word tensor is used in this chapter, and in previous meetings, there's been some debate over if this is actually a tensor. I believe the idea is that we're ultimately looking at outcomes, locations, and contexts, right? So it's this kind of outcomes by locations by context. So it does kind of, in a way, if you attempt to put it together, would be more of a tensor object as opposed to a matrix. It's a collection of matrices here. But hopefully that helps for anyone who's been wondering what that term, how that term's being used. Similarly, we have multiple B matrices because we also have multiple contexts related to location. Skipping ahead a little bit, or at least skimming the rest of this section, we have our C vectors, which are composed of preferences about location outcomes, which is C1. The rat disprefers staying in the same spot whenever it starts out. So it's set to a -1, right? You might expect that if you set that to 0 and kept them all 0, there's a chance the rat might just stay there for the entirety of the experiment, probabilistically. -1 kind of gets it moving. C2, meanwhile, has to do with the stimulus. 0, it's neutral towards not achieving any kind of stimulus. 6, because it really wants an attractive stimulus. -6, it doesn't want the aversive stimulus, right? It wants the cheese, it doesn't want, a tiny shock or something along those lines. And finally, just as far as the mathematics go, those are all passed through a softmax function. That allows you to both include positive and negative values whenever you're initially defining the vectors. And then also it normalizes everything such that we're looking at more like probabilistic probability distributions. So actually, after the math there, for example, the attractive stimulus is actually 400 times more probable, or we might say more desired, than the neutral stimulus. And then again, we have our D vector beliefs about, and again, it's factorized, there are multiple modalities. So the rat believes that it's starting at the starting location with full probability. That's how we set it. Meanwhile, for D2, that has to do with where is the stimulus that it wants. It doesn't know. So we have a purely uniform D vector there, half and half. So that experiment also includes things like a big part of it is there's a Q in the lower position of the maze. And so this is a great experiment to look at as well, because now we get to see both epistemic and pragmatic value. Epistemic, it doesn't know where the reward is. The Q gives it epistemic value. It gives it information about where the reward is, such as in the image there, the time step 1, rat starts at beginning location. Time step 2, rat moves to the Q at the bottom of the maze. The Q tells it that it's at the left position. That's the location of the reward. Finally, time step 3, smart rat follows that Q, moves to the attractive stimulus at the left position, which is pragmatic value, realizing its preference that it does want the cheese. So we end up with kind of this, 2-step process where it derives epistemic value from the Q, pragmatic value from actually achieving the attractive stimulus. So those are some key ideas in active inference in general. And yeah, again, kind of an exemplar model to wrap your head around, especially for those who are still kind of trying to understand the material here because there's a significant amount, but this is a great starting point for really trying to get into modeling. Section 7.4 of a model of information seeking. This is a kind of a saccade experiment where an agent looks at 4 different squares. This does start to break down things like it breaks down epistemic value further. Rather lengthy explanations of these terms, but they can be very important and they're very helpful for understanding the behavior. So those squares there, all the way to the left, this is where all of the squares are given equal epistemic value, right? They're the agent will look at any of them with roughly the same frequency. In the middle one, however, in that situation, the top left square is by the person who set up this experiment and its distribution. They gave the top left square more expected ambiguity, which is one of the terms that's derived from epistemic value. Beliefs about that square are less precise. They're more uniform in the A matrix for this square, the likelihoods. You can kind of equate this with the street light effect, the idea that if someone is out at night, they drop their keys, they don't know where they are, they will probably look where there's more light first. So the idea is, oh, it's expected that you will actually be able to minimize your uncertainty or reduce your uncertainty by looking at the other 3 squares here. Whereas the top left one, just imagine it's as if that square is blacked out or not well lit or dim or something, right? It's going to be hard to derive any kind of epistemic value from it because things are not very visible. So that's an attempt at getting at how to understand expected ambiguity. Then finally, top right, or excuse me, the rightmost image. Here, all of the squares are still visited, but the B transitions are made to be less predictable. And so it's the lower left, the lower left square is given a higher posterior predictive entropy. So the agent is less sure about what will be seen if the saccade is chosen for this square, if they keep looking there. It's as if they are unsure if there will be new information to get out of that square. So they keep returning to it again and again. Whereas for the other squares, those are more equivalent in the idea that, oh, you look at them, they don't really change. Why look back again, right? So it visits all of them, but it keeps checking out the lower left one. We do have box 7.1, which introduces us to, it's been mentioned before in the textbook, but this is just a quick rundown of trying to describe uncertainty and precision, or priors over precision. So that's a term that basically it's like gain control from the neural process theory that we've looked at previously, especially in chapter 5. This is kind of like amplifying, not adding to, but rather amplifying certain neural signals. Precision is inverse variance. So something has very high variance, it means it has low precision. Kind of hard to trust something that has very high variance or very low precision. Meanwhile, high precision means, oh, that seems more trustworthy whenever carrying out your computation. So it's in a sense, it's like weighting differently all of these different objects, the different matrices or particular beliefs or otherwise within the model. Section 7.5, learning and novelty. This is where we're introduced to beliefs about parameters. So this shows us, we're showing this on page 141, figure 7.10 or 7.10. It's basically the same model as before, except now we can see all these additional nodes where all of our different objects are parameterized. So our likelihood matrices, the A matrices, those are all parameterized by tiny a or small a. Same thing for the B matrices, parameterized by small b, C, small c, and so on. Those mesh really well with looking at things like precision, because we're looking at things like weighting. So these are all parameters that can be learned as well over the course of a series of experiments. And typically in active inference models, this learning occurs at a slower time scale, which is also kind of seen in the final example of this particular chapter, that has to do with hierarchical inference. But basically, these parameters can be learned as well, like how you can learn over time how much to trust certain likelihood mappings versus others, or trusting your beliefs about transitions versus others, or which policies to take versus others, things like that. Brief mentions about other things. I'll leave them off here, but it has to do with choosing conjugate priors whenever developing variables that are linked together, concentration parameters, the importance of Dirichlet distributions for categorical variables, where observations and states are kind of counted over the course of an experiment. The more you see this, the more you expect it to happen. It also helps us to remember that, like, a model, like how quickly it will update. So, you flip a coin 5 times, you see it's always heads. You might quickly come to a conclusion that it's an unfair coin. Meanwhile, if you flipped it 100 times with a 50-50 of heads or tails, and then you just happen on the next 5 tosses to get all heads, you're much less likely to think, oh, well, this is an unfair coin, because clearly it was pretty fair the first 100 times around, right? So by accumulating more counts, that informs us about how much the model or the agent might update its beliefs after the next new observation that comes in. We have a mention of structure learning, which is an entire topic on its own, and there's a lot of work still being done on structure learning, but it's rather interesting. I'll just briefly mention this is seen as something like offline learning. There's a metaphor used for it, like that it occurs during sleep. That is, the model or agent is not taking in any new data, and yet it's actually updating its beliefs. But more specifically, what it's doing is that it's scoring the model it currently has of the world, let's say, and during this sleep or resting offline state, it can actually compare that model that it has now with, let's say, a simpler model that maybe has removed some of the certain variables, or readjusted and minimized some of its matrices or otherwise, to see if it can produce an equivalently, if not better, performing model that nonetheless has some of its complexity reduced, and suddenly it's computationally more efficient, right? So basically, in a sleeper resting state, we have Bayesian model reduction, is one way that can occur, where the model is kind of pruned and improved, even though there's no additional data coming in at the moment. And then finally, section 7.6, hierarchical or deep inference. This again is very similar to the POMDP that we saw previously, except now we have an entire additional level added above. This is figure 7.12 on page 148. And so I would say briefly that the observation nodes in the middle between level 1 and level 2, that's a bit of a misnomer. What's going on is that the state inference occurring at the lower level is being fed up into level 2 as if they were observations at level 2. I note this because in a lot of other papers that I've personally read, usually they would not include those extra observation nodes in the middle. They would just go straight level 1 up to level 2. But this is a nice way of illustrating, like, it's as if those are observations for level 2. So what's going on? Well, we have at level 1 multiple time steps, like 3 time steps for every single time step at level 2. So this demonstrates that there are multiple time scales going on here. Level 1 is happening at a faster time scale. There's 3 time steps for every individual time step at level 2. The state predictions occurring at level 2 are being fed into the computations at level 1. And so it's like we have these descending predictions coming from this higher level. And then meanwhile, level 1's state inferences are acting as ascending observations, if that's useful. And so this is, I'll drop an article link into the chat, but I think that there's a rather nice paper that I've spent time reading, and I find personal interest in it. But it's a paper called Deeply Felt Affect, which came out a couple of years ago. And it relates to, I would say, fields like computational psychology or psychiatry. But why I think it's useful for anyone who wants some further reading here is that it, one, is a recreation of the T-maze experiment that we saw earlier. And on the other hand, it adds a hierarchical layer that is theorized in the paper to relate to emotion. And so we have a rat that is given this kind of emotional or affective layer to its model, and it actually dramatically changes its behavior whenever navigating the maze. It becomes much more confident depending on its emotion in its own model of how to achieve the reward. Sometimes to the degree that it will skip the epistemic value from the queue. It'll go straight to the reward. Why? Because now it gets an extra time step that it gets to spend with the reward. So it's again, it's just, we have the T-maze, we have a hierarchical model, and then finally we get to see how like behavior changes whenever we add this hierarchical layer. And whenever it comes to cognitive modeling, that's a big aspect, right? It'll be to kind of fiddle around with what variables do you need in your model, what are the layers to be included, and how do you kind of tune or prune things from there. I feel like I've spoken more than enough, so I will now open the floor if anyone has any thoughts or questions or just general things they're considering.
Sorry, where is the?
Is Prakash?
Actually, I have a very basic question. Since we have been talking on matrices, is the D vector just like a one-dimensional vector? That's it?
Yes. Yeah,
Nothing
that's
else, huh?
right.
Oh,
It-
wow.
So I will say so we saw the T-maze experiment, for example, and in that case, we did have 2 vectors, one for each modality. So the first one was, yeah, the rat's belief about where it starts, so the location factor or modality, and then D2, its beliefs about where the stimulus is. Is it to the left? Is it to the right? Here it's hard-coded as uniform as a starting point. But yes, they are each 1D vectors, and that's all you need to kind of kick off or start the simulation whenever you're running it.
Yes, so that is mapped to the number of factors of the B matrix, right?
Yes.
To the edge length of B.
Okay. Yeah.
Because B maps from hidden state to hidden state. So whatever the number of hidden states is, that B is just that per slice. And then the number of slices of B is equivalent to how many affordances there are. And then D is just the edge length that's carried through with S. And then A is O times S because it maps O and S. Pi is also a list with the probabilities of the actions in the policy space summing to 1.
Thank you. Yeah. I have one question. Sorry.
Yep.
In a actually when you normally try to initialize these vectors, say D, can you just also hard code it just one and then just pass it, right?
Yeah. Yeah, that's right. You would hard code it. That's one of the kind of theoretical discussions around active inference, right? It's more about the what and the why and the how, but not so much about how it starts. That said, what you can also do as far as learning and inference goes is you could have you could set up an experiment that runs over multiple trials. In that case, you would still hard code D, but going from trial to trial, you could have it such that the agent actually updates D over time. So that trial 1, it begins with those hard-coded values. Trial 2, it might update, now that it's the start of trial 2, what are its prior or initial beliefs about the state?
Yeah.
Yeah.
So like in this case, let's just say it was going to do 3 rounds of the T maze. And then initially it has a flat, it has it believes it starts in a certain setting. That could be that would be the D1 location, or maybe that one stays the same, the 1 0 0 0. And then the one it's like it learns by the end that it always starts on the right, or updates it towards the fact that that the reward or the stimulant food is on the right side. It could learn that by just counting up, okay, it was on the right, it was on the right, it was on the right. And then that kind of like putting pebbles of different color into the urn, that's the learning by counting, which is reflected here with a little d over the learning by counting of this one. So this one starts out 0 0, it starts out 1 1, and then you add 1 every time you observed it, and then that ends up that's a hyperparameter on the D distribution. So hence the kind of strategy of the book of showing like the minimal figure 4.3 type model. And then here's like one motif, which is hyperpriors for learning or attention, like Andrew mentioned. Here's another motif, nested models, but the hyperpriors are not shown. You can start to combine these, but then you can also imagine how the model's complexity grows a lot.
Sorry, what do you mean by motif?
Like here, the motif that it's showing is just nesting. It's not including little d. So it's not like this is not a generalization of the previous one.
Okay.
This is just like a generalization of the figure 4.3 one. As this one is, but this one's not nested. So like here, but the difference that it's trying to show is just about the idea of putting the italic lowercase above each of the letters. A, B, C, D, E. And then these motifs get kind of combined.
Okay.
Beginner
Jesse?
question.
Yeah.
Slightly tangential. So Andrew, in the React FX project that you're doing, are you building these types of models? I know it's very simple question.
Well, we've just kicked off the project a couple weeks ago, so we're still kind of trying to decide what kinds of models to build. But anyone who's interested can certainly, hop on and see what's going on. We do have a distinct coda for that, and so right now people are running project ideas, and so they're like in a table that you can just put in like, oh, I would like to try doing something like this, and then maybe put a couple notes on what direction you think it might take. And yeah, as Daniel's pulled up here, for me, I wanted to see if we could do a kind of reproducibility project where we take some of this, few years old code in MATLAB or SPM. Can we run it through Julia and ActInf instead? Just basically to see if we can help with reproducibility, and from there we could even potentially start moving into like modifying those models or maybe improving them or otherwise. But yeah, generally it seems like POMDPs might be one of the primary ways that we go, so hopefully that answers your question.
And is that all? I see Daniel posted the links in the chat, and I'll take a look. But is that all happening at this point asynchronously through Coda, or are there
Thursday
meetings on
meetings
Okay, that's what you
in
got up here on the
Discord.
screen.
And we're
Okay.
developing out the GitHub repo and so on. So there'll be, but there's more than ample async and synchronous opportunities if people want.
Okay.
And it's just like, I mean, and there's no chapter 6 for ActInf, but these are some of the I mean, we can go more into this another time, but we've like talked about how we can best contribute and write documentation. So for people
Right. So it's more, I
excited-
mean, it's still the, sorry, but it's still the underlying strategy.
Yes, we're learning this package for generative model. It's also over the course of the year going to increase a lot in its capacity and usability.
Okay, cool. All right, I'll pull up that coda. Thanks a lot.
And just to note, it'll also be incorporating some research that's been done since the publication of the textbook we're looking at. So there'll be a little bit more up to date, so to speak. The textbook is still a cornerstone of active inference, but that said, there have been some certain kinds of updates that have been made since then.
Yeah, I would just love to see this modeling applied with actual values, if you will, to help me wrap my mind around it.
Cool. Yeah, absolutely.
Thanks.
Good. I did notice Susan posted a question in the chat. How would reflection versus indecision be represented? I find that to be a rather interesting question myself. And while that's not directly answered by the textbook, surely there are papers that have been published on these kinds of topics. But in any case, intuitively, I would say just to kind of stay with the chapter itself. Page 145, 146. This is an agent navigating a maze. And in this case, the agent does not have any specified like particular preferences, or rather it's like purely uniform preferences. And so it's as if the agent doesn't prefer anything in particular. Whenever the model is set up in that way, then the agent engages in what could be viewed as an emergent behavior called novelty seeking, where it just keeps going to places that it hasn't been to yet. There's no preference for a certain reward or stimulus to where it knows that it wants to go to a space that has a reward, right? So it doesn't go there, it just goes everywhere. That said, it's still following the FEP. It's still minimizing expected free energy or variational free energy. And so it will avoid spaces it's already been to because it's already been there. Nothing new to get, no new epistemic value to be derived from a space you've already been to. And so it will just kind of like run the full gamut of all the spaces it's never been to. This is a phenomena that's also been referred to by Posner in 1985 as the inhibition of return. So that's a pretty interesting thing to see, and it makes a lot of sense because whenever we look at our equations, the C vector or preferences are heavily informing G, and so if there's nothing informative about C because it's purely uniform, nothing's particularly preferred, then it doesn't really help with figuring out what to do other than just keep running around getting all that novelty you can. Maybe it's thrill seeking. It's a joke, but reflection, meanwhile, not so sure. Intuitively might have a relationship with structure learning. An agent doesn't necessarily have to be sleeping in order to kind of tune or prune its model. But the idea is that, yeah, there's no incoming sensory data. So reflection might relate to that process, someone who's sitting there reflecting, kind of thinking things through, even though they've not been presented with anything new. Might be a form of structural learning. There might be a paper out there, or a dozen on these kinds of things worth searching for that. But yeah, very interesting question. Yes, Anna, Magdalene. I see you put your
You're
hand down.
muted, Magdalena.
Can you hear me okay now?
Yes.
Okay, sorry about that. Yeah, I was wondering if you could elaborate on a little bit on the offline updating of beliefs. And I'm curious about the scientific studies that have been done demonstrating that this in fact happens, that you're during sleep or maybe meditation or daydreaming, right? Can you elaborate a little bit on how active inference scientists have looked at this aspect of active inference?
So I'll just be direct in saying that, yeah, I'm not personally too sure of the research that's been done very specifically on structured learning in relation to actual sleep or meditation. I mean, I'm seeing just from a quick.
I'll show one. This is not exactly ActInf, but it's right there. I'll put it in the notes. This is kind of there's many similar architectures done in machine learning where there's this phasic approach, extending and updating during the day with a fast inference, and then using different techniques for sleep. And I mean, it probably gets into the specifics of the machine learning architecture. And then also there's the whole other angle you said, like empirically, what's happening at the synaptic level and at like the cognitive level for humans, and skill consolidation and sleeping, learning consolidation, naps. There's probably a lot of different phenomena like that.
Thank you.
Just drop this here, but this looks to be a manuscript by a couple of researchers as well who make a mention of particular meditative traditions. But they claim there that as opposed to it being structure learning per se, they claim that meditation is more of a form of, like, it's a peculiar policy itself, that is you're choosing to do that. That actually looks to be a really interesting paper, and I appreciate that there's a more kind of culturally accurate as opposed to highly abstract kind of theme to it. So, yeah, Susan.
So yeah, this is fascinating. Thank you, Andrew. So what keeps coming up is the reference to, learning takes time, or there's no fast learning, and so I'm wondering if maybe the concept of learning itself is more specific than, I guess, um, what we generally think about learning. So, I mean, how would you categorize learning, or well, maybe why it keeps referencing that learning is slower than what?
Yes, this is a great question. I'll give a first thought. Especially as more complex cognitive models are built, there's several ways that different timescales of adaptation happen. So the fastest layer is called inference, and that's kind of like the rubber hits the road, like each new observation coming in, but also the whole process is called inference. But also the fastest layer is called inference. Then the next slowest layer is attention. So like attention modulates on over multiple sensory cycles, like just thinking about the visual case or the dinner party, like overhearing multiple conversations. Like attention modulates faster than or slower than the words coming in, but faster than updating like deeper factual beliefs. And then learning, as distinguished from those other kinds of parameter changings, is like here being modeled explicitly with these hyperpriors and updating the distribution that the kind of rubber hit the road parameters are being drawn from. That's not the only way to model learning. So hence chapter 6 and really digging in with like what timescale analysis is being studied, because maybe whether it's learning over seconds, like repeating back a phone number, or whether it's like a semester level, maybe that's the time scale of your model. So then that learning is happening on the kind of primary time scale of the model. It's just way too general to say without specific system of interest. But that being said, there are multiple ways that like to kind of, and the hierarchical models like looked at. So multiple non-exhaustive or exclusive ways to model the multi-scale temporal dynamics of change.
Yeah, I would definitely second Daniel's point about, yeah, there is no single answer to the question. Again, we have this final example in this particular chapter referring to, yeah, words and sentences, right? So those timescales don't seem dramatically different, actually, right? Like we're looking at a matter of, let's say, milliseconds versus seconds. Like predicting what the next few words are going to be in an entire sentence to try and capture something like what the sentence is about versus the faster timescale of word, like word to word in the sentence. But I did want to mention a couple other as far as like trying to map this to concepts or behaviors in neuroscience. Another way of thinking, not necessarily thinking about it this way, but one potential analogy could be something like working memory versus long-term memory, right? Like here's your quick access, like working memory of the moment by moment. Long-term memory occurs over time, it gets consolidated slowly over time, and it can lead to long-term changes in things like your daily habits, what comes more naturally or quicker to you. So it just describing it a bit more intuitively that way. Yeah, I like to sometimes think of it as like, yeah, short-term versus long-term memory. Then in addition to that, as we saw in chapter 5, in terms of the neurobiology, it's commonly been found or theorized from various studies when working with neuroimaging data that whenever a participant in these studies is learning something, what happens is that you tend to find when looking at brain rhythms from, let's say, EEG, that more theta and gamma waves are present simultaneously. And so they view it as what would be called a theta gamma coupling. We do get a reference to that in chapter 5 in this textbook. Theta rhythms are slower in a particular kind of rhythm band or frequency band. Gamma are faster. And so what happens is these rhythms kind of it's kind of fun. You can think of it as like music, you have some fast drums and a slow piano, or some such thing. But there's a kind of syncing between these two differing rhythms, and it is seen as being a kind of neural correlate to someone learning something. So multiple time scales in a POMDP, multiple time scales in how our memory works, multiple time scales in neuroimaging data. And just a couple more kind of metaphors as food for thought.
So one more question that it almost, I think I'm wrong, but it almost makes me want to wonder if the learning in this sense isn't an effect of actually acting on a policy, but that may or may not be correct. But the other thing that comes to mind would be, would surprise occur at either level? In other words, if they don't learn, or if their policy doesn't get the expected payoff, then there would be a surprise. But also learning could actually encompass a surprise as well. So it makes me want to say that there's almost a surprise tolerance.
Yeah, like thinking back to the chapter 2, the Bayesian surprise is the delta of learning. And so
Okay.
if the hyperpriors are fixed, the Bayesian surprise is going to be 0, no matter how surprising in the first sense the observation is. Like, we think that the room is this temperature and we're not open to learning. We've fixed hyperprior, and then even shocking observations just continue to shock us. Versus if you had like a kind of adaptive learning rate, then there would be some, like, a surprising observation would come in that would catch your prior wherever it initially was, and then that would also move your prior some amount over to the new observation, so that if that kept happening, eventually, like, you would converge so that that was no longer surprising. And then how fast you converge is attention slash the learning capacity over different time scales.
So learning capacity would come into the level of tolerance, I guess. Would coincide. Yeah, thank you.
And forgive me, to clarify, so learning capacity is represented through those hyperpriors?
Yeah, indirectly, yes. Like when Andrew mentioned the coin flip, it's like when and this is just you could see this in any kind of Bayesian statistics overview. Like, if you only had flipped a coin twice and you got 1 and 1, then you'd have a wide prior centered around 50%, because your maximum likelihood estimate for the fairness of the coin is 50-50, but it's very dispersed. It can't be 0, can't be 100, because you know that you've seen at least the other things, but it's broadly, like, it's a very over dispersed. And then if it was 1 million and 1 million, then the 2 millionth and 1 flip would be very tight, would only move the distribution a tiny amount. So that's like that learning by counting, and then as you count up more, and then you have this whole question of, okay, well then, but then that just slows down our learning rate. but maybe it's a cell differentiating and it does slow down its learning rate to a halt. Or maybe there's another process that takes a look at that learning by counting variable and says, when this is 100, we cut it down to 20. And that's this whole challenge with the iterated modeling, is figuring out all these like second order rules and diagnostics to be like, okay, should we cut it down to 20 or like 30? And then those are all these like simulations and sweeps that you do, and then investigate how the agent is behaving in different regularities.
Got you. Thank you. That's a good explanation. That's a lot of compute.
It is. So even, and that's one very interesting thing, which is like, even when like the model as parameterized might be low compute to run, the open question is how much did it take to get there? Not dissimilar to like a language model, where in the forward running of a trained model, it's not mega computationally expensive, but then training it can be expensive. And similarly, while updating the model might not be expensive. So for a toy model, where just whatever you make, you let it run and it's all good. But to find like adaptive and resilient ranges of parameters with many, many possibilities, that can be running these models many times. Cool. Well, we return for chapter 7, part 2 next time, or feel free to join chapter 2. It's kind of funny. Chapter 2 and chapter 7, they are very similar. And in chapter 2, we kind of reference chapter 7 because that's where the discrete time models are. Then chapter 7 took us back to chapter 2 with the surprise and everything. So, oh, thank you, Cheryl. I'm going to copy this in.
You're welcome.
Thank you. Okay, farewell. Bye.
Bye bye.